Welcome! In this session, we'll explore an interesting problem, palindrome number, where we'll determine if a given integer is a palindrome without converting it to a string. We'll look at different approaches, their trade-offs, and complexity. Let's dive right in. In this problem, we need to determine whether an integer is a palindrome. A number is considered a palindrome if it reads the same backward as it does forward. For example, the number 121 is a palindrome because reversing it still gives 121. The task here is to write a function that takes an integer input, x, and returns a Boolean value, true if x is a palindrome, and false otherwise. The input format is straightforward, it's just a single integer, and the output is a Boolean indicating whether the number meets the palindrome condition. Let's look at some examples to understand this problem more clearly. In the first example, the input is x equals 121. The function should return true because when the digits of 121 are reversed, you still get 121. This symmetry makes it a palindrome. In contrast, consider the second example, where the input is x equals -121. While the digits of 121 itself might seem symmetric, the negative sign at the front causes the reverse of the number to become 121-, which is not the same as the original. Therefore, negative numbers cannot be palindromes, and the function returns false in this case. Now, take a look at the third example, where x equals 10. Here, reversing the digits gives 0, 1, which is not the same as the original number. As a result, the function returns false because the number does not satisfy the palindrome condition. On the other hand, if the input is x equals 0, the function returns true. This is because reversing a single-digit number always results in the same number, making it a palindrome by definition. To summarize, the number 0 is a palindrome because it reads the same backward as forward. Additionally, there are a few constraints and edge cases to consider. For instance, the input number must lie within the 32-bit signed integer range, which is from -231 to 231. Negative numbers are inherently not palindromes because of the negative sign. Single-digit numbers from 0 to 9 are always palindromes. Some tricky cases include numbers with trailing zeros, like x equals 100, which cannot be a palindrome because reversing it gives 001. Finally, the problem requires solving this without converting the integer into a string, which adds an extra layer of challenge to the implementation. To solve the problem of determining whether a number is a palindrome, we first consider the brute force approach, which involves converting the integer into a string. The intuition here is straightforward. By reversing the string and comparing it to the original, we can check if the number reads the same forwards and backwards. The steps are simple. First, convert the number into a string. Then, reverse the string and compare it with the original. If they match, the number is a palindrome. This method has a time complexity of O, n, where n is the number of digits in the number, because reversing the string requires processing all characters. However, it also has a space complexity of O, n, due to the memory needed for the string conversion. While this approach is easy to implement, the downside is that it uses extra memory, making it less suitable for very large numbers. A more efficient solution is the optimized approach, which involves reversing only half the digits of the number. The core idea is that a number is a palindrome if the digits in the first half match the digits in the reversed second half. By reversing only half the digits, we reduce the amount of processing and memory required. To implement this, we first handle edge cases, such as negative numbers or numbers ending in 0, which cannot be palindromes unless the number is 0 itself. Next, we initialize a variable to store the reversed half, and while the original number is greater than this reversed half, we repeatedly extract the last digit, append it to the reversed half, and remove it from the original number. Once the loop ends, we compare the original number with the reversed half. For odd-length numbers, we can ignore the middle digit by dividing the reversed half by 10. If the two values match, the number is a palindrome. This optimized approach is highly efficient. Its time complexity is O log 10 x, as we only process half the digits of the number, and its space complexity is O 1, since it uses only a few variables. The trade-offs are clear. On the positive side, it is both time and space efficient, and it avoids the need for string conversions. However, the logic is slightly more complex compared to the brute force approach. Another alternative to consider is reversing the entire number instead of just half. Here, we reverse all the digits of the number and compare the reversed result with the original. Although the steps are straightforward and avoid string conversion, this method processes all digits, making it less efficient than reversing half. Its time complexity is O log 10x, like the optimized approach, but it doesn't benefit from the reduced processing of half the digits, making it less optimal overall. When we analyze the alternative approach of reversing the full number, we see that it has a time complexity of O log 10x, as it processes each digit of the number. Its space complexity is O1, as no extra memory structures are used. The advantage of this method is its simplicity. It avoids string conversion and uses clear, straightforward logic. However, compared to the optimized approach, it is less efficient because it processes all the digits of the number rather than stopping after reversing half. This trade-off makes it a less ideal solution when efficiency is a priority, even though it might be easier for some to implement or understand. The chosen strategy for this problem is the optimized approach, which involves reversing only half of the number. This method is the most efficient in terms of both time and space, as it processes only half the digits and avoids the overhead of string conversion. While the brute force approach is quicker to implement, it uses unnecessary memory and is less suited for large numbers. Similarly, reversing the full number is simpler to understand but less efficient than the optimized solution. The key insight here is recognizing that only half the digits need to be reversed to determine if the number is a palindrome. This reduces computational load while maintaining accuracy. Overall, the optimized approach strikes the right balance between efficiency and readability, making it the best choice for solving this problem. The problem we're solving is to determine whether a given integer, x, is a palindrome. A number is considered a palindrome if it reads the same backward as it does forward. For instance, the number 121 is a palindrome because reversing its digits results in the same number, but 123 is not because reversing it yields 321. One approach to solving this is by leveraging string properties. First, we validate the input by checking if the number is negative. Negative numbers can never be palindromes because they include a dash sign, which disrupts symmetry. For any non-negative number, we convert it into its string representation using the str function. This transformation allows us to work with the digits as characters. For example, the integer 121 becomes the string 121. This conversion makes it easier to manipulate and check for palindromic properties. After converting the number to a string, the next step is to reverse the string. In Python, this can be done efficiently using slicing with ::-1. For example, reversing 121 results in 121, which is identical to the original string. On the other hand, reversing 123 produces 321, which is clearly different. Once we have the reversed string, we simply compare it to the original string. If they match, the number is a palindrome. If not, it isn't. Finally, we return the result of this comparison. If the two strings are equal, we return true, indicating that the number is a palindrome. If they're not equal, we return false, indicating that it isn't. This straightforward approach leverages Python's powerful string manipulation capabilities to efficiently solve the problem. This approach comes with several key insights. First, reversing a string using slicing is both concise and efficient. It operates in O(n) time, where n is the length of the string. This is because each character is accessed sequentially in reverse order. Additionally, we exclude negative numbers right away, as their dash sign prevents them from being symmetrical. For example, -121 cannot be read the same forward and backward. There are also some interesting edge cases to consider. Single-digit numbers, like 0 or 7, are always palindromes since they read the same both ways. Numbers that end in 0, such as 10 or 100, cannot be palindromes unless the number is 0 itself. Finally, even very large numbers, such as 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1, are handled efficiently due to the linear nature of string slicing in comparison. To dive deeper, the algorithm primarily relies on the use of strings to represent and process the number. Strings are ideal for this task because they simplify both the reversal and comparison operations. Let's break down the key operations and their complexities. First, converting an integer to its string representation takes d time, where d is the number of digits in the number. Next, reversing the string using slicing also takes d time, as each character is accessed once. Finally, comparing the original and reverse strings is another d operation, since it involves checking each character sequentially. Together, these steps ensure that the algorithm is efficient and well suited for this problem. Now, let's summarize the overall complexity of this approach. The time complexity is d, where d is the number of digits in the number. This is because each of the key operations, conversion to string, string reversal, and string comparison, takes linear time. The space complexity is also d, because we need additional space to store both the string representation of the number and its reversed version. To illustrate how the algorithm works, consider the input x equals 121. We first convert it to a string, resulting in 121. Reversing the string gives 121, which matches the original, so we return true. For a negative input like x equals -121, we check if it's negative. Since it is, we immediately return false without further processing, as negative numbers cannot be palindromes. Finally, let's look at one more example to solidify our understanding. If the input is x equals 123, we start by converting it to a string, resulting in 123. Reversing the string produces 321, which does not match the original string. Therefore, the comparison evaluates to false, and we conclude that 123 is not a palindrome. This example highlights how the algorithm quickly identifies non-palindromic numbers by leveraging simple string operations. With these steps, we've covered both the logic and the efficiency of this approach to solving the palindrome number problem. The provided Python implementation solves the problem of checking whether an integer is a palindrome. A palindrome is a number that reads the same forwards and backwards. The function isPalindrome is defined within a solution class, as is standard for LeetCode problems. It takes an integer x as input and returns a boolean indicating whether the input is a palindrome. First, the function checks if the number x is negative. Negative numbers cannot be palindromes because they have a dash sign at the beginning, which would not match any reverse sequence. If x is negative, the function immediately returns false. Next, the integer x is converted to its string representation using Python's built-in str function. This allows us to easily manipulate the number as a sequence of characters. The reverse of the string is computed using slicing with the ::-1 syntax. This creates a new string where the characters are in reverse order. Finally, the function checks if the original string representation of x is the same as its reversed version. If they are equal, it means the number is a palindrome, and the function returns true. Otherwise, it returns false. This approach is efficient for the problem at hand. Converting the number to a string and reversing it both operate in n time, where n is the number of digits in the number. This keeps the solution simple and clear while handling the palindrome checking logic effectively. This is the Java implementation of the palindrome number problem, LeetCode number 9. The logic mirrors the provided Python solution, converting the integer to a string, reversing it, and checking if the reverse string matches the original. Key differences include Java's need for explicit type declarations, the use of integer to string for conversion, and string builder for reversing the string. To solve the problem of determining whether a number is a palindrome, let's walk through an example where the input is 121. First, we check if the number is negative. Since 121 is not negative, we move forward to the next step. Here, we convert the number into a string representation using the code original equals str x, which gives us the string 121. Once we have the string, the next step is to reverse it using slicing, reversed_str equals original, ::-1. This produces the reversed string, which is also 121 in this case. Finally, we compare the original string with the reversed one using the condition original equals reversed_str. Since both strings are identical, the function returns true, confirming that 121 is indeed a palindrome. Now, let's consider another example where the input is -121. Again, the first step is to check whether the number is negative. Since -121 is negative, we can immediately conclude that it is not a palindrome. This is because negative numbers include the negative sign, which makes them read differently backward. For example, reversing -121 would result in 121-, so it cannot be the same. As a result, the function directly returns false without any further steps. This highlights an important optimization: negative numbers are never palindromes, so we can skip the string conversion and reversal entirely. Next, let's analyze the case where the input is 123. As usual, we start by checking if the number is negative. Since 123 is not negative, we proceed to the next step. Here, we convert it to a string using original equals strx, resulting in the string 123. Afterward, we reverse this string using slicing, reversed underscore str equals original, ::-1, which gives 321. The final step is to compare the original and the reversed strings. Since 123 is not equal to 321, the function returns false. This indicates that 123 is not a palindrome because its digits do not read the same backward as forward. To summarize, this solution first checks if the number is negative, since negative numbers cannot be palindromes. For non-negative numbers, the approach involves converting the integer to a string, reversing the string, and comparing the reversed string to the original. If the two are equal, the number is a palindrome, otherwise, it is not. The time complexity of this solution is O(n), where n represents the number of digits in the number. This is because reversing the string involves iterating through all the digits. Overall, this method is straightforward, leveraging string manipulation to determine whether a number is a palindrome efficiently. To analyze the time complexity of our solution, we can break it down step by step. First, the negative check using if x less than 0 is a simple condition that evaluates in constant time, contributing O(1). Next, the operation strx converts the integer to a string by iterating over all its digits. The number of digits, denoted as d, is proportional to log 10x, so this step contributes O log 10x to the time complexity. Following this, the slicing operation original, ::-1, creates a reversed copy of the string, which also involves iterating over all d characters, contributing another O log 10x. Finally, the equality check original equals reversed underscore str compares two strings character by character. In the worst case, this requires comparing all d characters, adding another O log 10x. Together, these operations form the foundation of our time complexity analysis. When we sum up the contributions from each step, we have O(1) for the negative check and 3O log 10x terms from the string conversion, reversal, and comparison operations. Adding these together simplifies to an overall time complexity of O log 10x. Now, looking at space complexity, the first major contributor is the string conversion strx, which creates a new string representation of the number. This requires O(d) space, where d is the number of digits in x, or equivalently O log 10x. Similarly, the string reversal original, ::-1, creates another string of the same length, contributing an additional O log 10x space. Besides these, the solution uses a few variables like original and reversed underscore str, which occupy constant space, O(1). The total space complexity is therefore dominated by the two strings we create, original and reversed underscore str. Each requires O log 10x space, making the overall space complexity O log 10x. Comparing this solution to other approaches, a brute force method might involve manually extracting digits using arithmetic operations like division and modulo. While this approach also has a time complexity of O log 10x, it could save space by avoiding string operations entirely. However, manual digit extraction is less readable and more error-prone. Alternatively, an optimized approach could reverse only half of the number and compare it with the other half. This would reduce the space complexity to O(1), as no strings are created. However, the time complexity remains O log 10x, since we still process all digits in the number. To mathematically validate our big O analysis, consider that the number of digits in a number x is proportional to log 10x. This is because the base 10 logarithm effectively counts the powers of 10 required to represent x. Each operation in our solution, conversion, reversal, and comparison, processes all digits in the number, leading to a time complexity of O log 10x. Similarly, the space complexity is determined by the storage required for these digits in string form, which is also proportional to log 10x. Thus, both the time and space complexities of this solution are conclusively O log 10x. When solving the palindrome number problem, there are some common mistakes to avoid. First, many solutions fail to handle negative numbers correctly. Remember, negative integers like -121 are not considered palindromes because their reversed form will not match the original. To address this, you should explicitly return false for any negative input at the start of your function. Next, be cautious about using extra space unnecessarily. Converting the number to a string and then reversing it might seem straightforward, but it requires extra space. A more efficient approach involves reversing the digits mathematically in place, which avoids this overhead. Finally, watch out for integer overflow when reversing numbers mathematically, especially in languages like Java or C++ where integer types have fixed limits. If you reverse a number and it exceeds the allowable range, it could lead to runtime errors or incorrect results. To mitigate this, use data types like long where needed, or ensure the reversed number remains within valid bounds during computation. Another important consideration is handling single-digit numbers. Numbers from 0 to 9 are always palindromes, but some solutions overlook this and fail to account for these cases. To fix this, simply add a condition to return true for any input between 0 and 9. Also, reversing the entire number is often unnecessary. For improved efficiency, you only need to reverse half of the digits and compare them. This reduces redundant computation and speeds up your solution. Now, in interviews, there are a couple of patterns to watch for. Palindrome problems frequently involve symmetry, so it's helpful to understand how to identify and manipulate the middle point of your input, whether it's a string, number, or array. Additionally, interviewers often prefer solutions that optimize for space, so they might ask follow-up questions about reducing memory usage. To set yourself up for success, clarify important details with the interviewer, such as whether negative numbers are allowed or what the maximum input range is. These questions can help you prepare for edge cases like integer overflow. It's also useful to understand the trade-offs between different approaches. For instance, a string-based solution is simpler to implement, as it involves converting the number to a string, reversing it, and comparing. However, this approach requires space, which may not be ideal. On the other hand, reversing the number mathematically avoids this extra space but can be slightly harder to debug. Another common follow-up is how to handle cases where the input isn't strictly a number, such as when it's a string. For example, how would you deal with spaces, punctuation, or differences in letter casing? Additionally, interviewers might extend the problem to other data structures, like linked lists, and ask if you can adapt your solution. For further practice, there are several related problems to explore. LeetCode 234 involves checking if a linked list is a palindrome, while LeetCode 125 extends the concept to strings with additional constraints like ignoring non-alphanumeric characters. For a more advanced variation, you can look at LeetCode 5, which focuses on finding the longest palindromic substring in a string. When considering alternative approaches to solving this problem, there are three main methods to explore. The first is the string-based approach, where the number is converted to a string, reversed, and compared with the original. This method is simple to implement and has a time complexity of O(n), but it requires O(n) additional space. The second approach involves mathematical reversal. Here, you reverse half the digits of the number in place and compare them. This method is much more space efficient, using only O(1) extra space, and has a time complexity of O log 10n, but it can be slightly more challenging to implement. Finally, there's the recursive approach, where you extract and compare digits recursively. While this method is elegant, it has O(n) space complexity due to the recursion stack, making it less efficient in terms of memory. Each of these methods has its own trade-offs, so your choice should depend on the constraints and requirements of the problem. Great job! Today, we covered the palindrome number problem, including a brute force and optimized approach. Remember to consider both time and space efficiency in your solutions. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!